Okay, so in the last video we went over the repressible operon models and like the basics of operons and what an operon is. So I'm not going to go over that again in this video because I'm assuming you already watched that one. If not, go back and just watch the initial parts of that video to understand. But we're going to jump right into the inducible operon model. So in this model, it functions very similarly to the repressible model, except everything is basically in reverse. So in this model, an example of the inducible operon model is the LAC, standing for lactose model. And that's what we're going to be going over real quick in this operon model. So this operon is like, unlike the repressible operon, this one is almost always off. And what that means, same thing, and that is because there is almost always a repressor that is binded to it at all times. So this repressor, it fits here into the operator, and it keeps this gene pathway, this operon, off at all times. Well, not at all times, but most of the time, 90% of the time. So what is this pathway for? So this pathway codes for the lactase enzyme, and that is an enzyme that breaks down sugar. So when it is on, it produces lactase. I have the inhibitor still here, but know that when it is on, it produces lactase. So when it needs lactase to break down lactose. So what happens is when those lactose concentrations are high, this gene pathway, it needs to be turned on so that we can break it down and convert it into energy. So it is quite literally the opposite of what is going on in the repressible model. So in the repressible model, the repressors were made in an inactive form, but in this model, they are being made in active form. As we can see here, they're made and they can fit into this operator immediately. But what happens is when the lactose concentration goes up, same thing, the lactose will bind to the active repressor. That will cause a shape change. And because of the shape change, they will together break off of the operator, and that will cause the pathway to turn on, and this lactase enzyme will be produced. So as the lactase enzyme is produced, the lactose sugars begin getting broken down, the concentration starts falling, and then it reaches low levels, almost zero. And once the levels are extremely low, what's going to happen? A lactase enzyme will come here, it will break this bond here, and it will change back to its original shape. I didn't show the shape change because I think you watched the other one and saw how I drew that out. But this will go back into its active state, and then it can come back and bind up here to the operator. It will turn the gene off, and that's pretty much it. And so then we will erase up here the lactase being produced because the gene is off. The lactose concentration is at zero or very, very low because we do not need lactase enzyme anymore. And that is pretty much it. And now because the lactose here is not actually the product, unlike tryptophan in the last pathway, this is actually the substrate. So we call it the inducer. Go, inducer. And these inducible operons are usually used for exergonic breakdown of molecules, as we just saw with the enzyme breaking down the lactose into energy. And yeah, pretty much it for the inducible operons, and that covers both of the operons. And those are two big examples that you need to know when we're talking about prokaryote gene regulation. Hopefully that made sense. I'm going to keep going over some more topics. And yeah, that's it.